Right. Okay. Yeah, and thanks for inviting me as well to give a talk on Linaro Forge. So my name is Rudy Shand. I'm a principal field application engineer at Linaro. And pretty much I've had backgrounds in debugging and profiling for about 12 years, but in the HPC space around 8 years. Yeah, so the tool that I'm working on is Linaro Forge, and we can discuss what that is. So Forge from a high level is a HPC development solution toolkit from Linaro. And this is comprised of three distinct tools. So we have DDT. This is the highly scalable debugger, and you're able to debug anything from single process all the way up to hundreds of thousands of processes. And really, the debug is built from the ground up to be scalable. So you can particularly debug things around multi-threaded application, typically using MPI or SBMD type codes. And when we talk about scalability, we're talking about the user interface is quite scalable. So if you think about you running all these different threads, if you have OpenMP threads, for example, as well as MPI, I mean, this can be quite challenging to put on a user interface for you to know where your threads are, what your processes are doing. So scalability in the sense that everything looks quite compact and you're able to see what your application is doing, even at very high scales, as well as being able to scale up to a whole range of different processes. So we can scale up to hundreds of thousands of processes and the tools doesn't fall over. So the second tool is MAP, and this is a source level sampling based profiler, which means you run your application as you would normally run it. You append map to it, and then it will start collecting samples to profile your application. And you get performance information on a line level, so you know which line is causing, say, an MPI imbalance or where your time is being spent on each line. And MAP is actually built on the same scalable framework as DDT. So again, you can run at very high scales and you'll be able to collect samples. Then the third tool is performance reports. And performance reports pretty much takes all your map data and just gives a one high-level summary of your performance application. So it tells you things like if you're MPI bound, if you're compute bound, and it gives information on your I/O. And performance reports also gives hints and tips. So if you're not necessarily aware of where to start with performance, you can run a performance report. It will tell you if your application is running performantly and hints and tips of where you should focus. So then looking at some of the supported platforms. So let me just get this up. So this is for debugging. Profiling is slightly different, which we'll talk about a little bit later. But in terms of supported platforms, we support all the CPU architecture, so Intel, AMD, ARM, as well as all the GPU accelerators, so AMD, CUDA, as well as the Intel Z HPC. So if you're running a example on Polaris or on Aurora, you'll be able to debug it in the same way. It also support all the major operating systems and a whole range of MPIs and compilers and programming models such as SYCL, OpenMP, OpenACC, and all of those as well. Then in terms of languages, support C, C++, Fortran, as well as Python, and then also a range of different startup mechanisms like Cray Powell's, which is what has been used on Polaris. But the main takeaway here is that it doesn't really matter which hardware architecture you're running on, which system you're running on, the debugger will work. So if you're used to it running on one system, you can port your knowledge onto any system. And we'll talk a little bit later, but the only difference between debugging and profiling in terms of supported platforms is that we don't support profiling on the Intel Z HPC. So on Aurora, we only support debugging, but Polaris will support debugging and profiling. So when you run your application and you set up this to debug with DDT, you typically get a user interface that looks like this. So if you look at it from sort of a high level, it just looks like a normal debugger. You can run, you can pause, you can step, as you can do with other debuggers. But where DDT stands out is that you're able to see what's going on with all of your processes, and it gives some of this UI for scalability. As an example, when you look at some of your locals, you can see in the value is these spark lines. And what the spark lines are busy showing is how that variable value is distributed across all of your processes. So you can see with my rank, that's kind of going up linearly. P is a flat line, which means that all the processes are the same value of 512, for example. And then you can create groups as well. So you can step different groups and evaluate your variables as well. And the nice thing with the evaluating as well is that if you have got a complex calculation, you can calculate that within DDT and calculate each part of that calculation, as well as add new values into that. So you can sort of transpose some of your values to see if this value was there, how would that change how the application runs. So you can play around with the locals and the values that are in there. And we'll go through this in a little bit more detail as we go through the hands-on session, but the main takeaway here is that it's just a general debugger, how you'd normally debug, but DDT gives some additional information to debug across processes and threads. So looking at a high-level overview of some of the features, and notice this isn't all of the features, this is just some of the highlights. So one of the features we have is around the trace points. And what trace points is kind of like a scalable print statement. So instead of you writing a print statement in your code, having to recompile it, what you can do in DDT is just add in a trace point. You can tell it what variable value you want to trace, and then as your application runs, it just prints that to a window in DDT for you to see how that variable value is changing over the execution of your program, without needing to recompile your code or remember to get rid of print statements afterwards. So as we discussed, there's spark lines, and with trace points, you get these spark lines as well. So you can see how that variable value is distributed across all of the different processes. And if there's any outlier, you'd be able to see that. So one of the second features is watch points. So if you think about breakpoints, what breakpoints does, it holds at a specific location. So this could be a line or a function. And watch points, on the other hand, they halt on the value of an expression. So you can say if this variable value is more than a specific value, then DDT will halt. And so using breakpoints and watch points interchangeably helps you to kind of set stops in your program at either locations or at variable values. And then we also have static analysis, and the static analysis kind of look at things like uninitialized variables. You can find memory leaks and those kind of issues, which before you even running your application, you can see if there's any issues. And it's a good practice to fix up anything that comes up with a static analysis. Because when you're running this on, say, 2 or 3 processes, it might be fine, but as you scale your application up, these issues might get worse and start causing crashes or different race conditions further down the line. And finally, there's memory debugging. So memory debugging allows you to detect reads or writes that's outside of your defined array. It also gives you a visualization of how your memory is being utilized across all of your processes. And it just gives this visual representation of your memory. So if, say, process 0 is using a lot more memory than you expect, then you'll be able to see this outlier. And you're also able to click on that view to go to the exact source code where that memory is being utilized. So you can really dig down into your memory of your application. So as well as CPU debugging, the tools also support GPU debugging. But there are some differences between CPU and GPU, mainly around the implementations. But the look and the feel is exactly the same. The only difference is that when you step inside of a kernel, or you set a breakpoint inside a kernel and run to that breakpoint, as you're in that kernel, DDT will open up a couple of extra windows. So it will open up the kernel progress view, the parallel stack view, a thread selector, and the GPU device pane. And what the GPU device pane does is it just tells you which GPUs you're connected to, how many threads are available. It just makes you aware of what you're actually connected to. But there are a couple of things you need to be aware of. So with the Intel Z GPU, the smallest execution unit is a subgroup, and this could be 8, 16, or 32 threads. I'm not actually sure how these are set. I think they hardware specific. So I know on Aurora it's 16 threads. So as you step, it will step 16 threads at a time. But I'm not sure if you can set these through software. So all of these threads within a subgroup, they execute in a lockstep, which means you can't step one thread at a time. You have to kind of step 16 threads at a time. And when you press play or continue and you hit this breakpoint, it's not possible to run individual subgroups or threads. All of them run it at the same time. So as soon as you press play, all of your threads will run. As soon as you hit a breakpoint, all of your threads will halt. So those are some of the specific implementations that you need to be aware of. And the same is with NVIDIA GPUs or AMD GPUs. So then looking at the progress bar. So what this progress bar is, it's a projection on a straight line of the GPU block indexing system. So if you look at all of your GPU threads on the block indexing system, as you click through those, you can bring some of those threads to the front. And because they're selected, you can see what all the variables are for those threads. And you can evaluate some of those expressions as well. So anything is green is the threads that are currently active. So these are the ones that are busy running on the GPU. If it's white, it means that they're not been scheduled yet. And it could be there could be two reasons for this, actually. So if they're not scheduled to run, it could be because they've already run and they've just completed, or it could just be that they've not run yet. So you have to wait for them to be scheduled for them to turn green as well. And so once this kernel completes and you go back to your host code, then you see the debugger as you would normally see it. And to be able to debug this, you need to compile your application with minus lowercase g as well as minus O0 flags. And this just gives the debugger enough information to debug the GPU. So along with that, we also have the stack view, and this gives you a different representation of debugging. So if you click on one of these stacks, then you can see the location and the number of threads. And you can see, well, we're running the main function with 39,000 threads. We've gone to another one which is running 7,600 threads. And then because we stepped one of these threads, those 16 are stepped into lockstep. So we can see that there's a deviation in the code. So we know where all the threads are. And then we can also look at the GPU thread ranges as well as the size of each range. So apart from GPU debugging, we also support Python debugging. So even Python debugging on the GPU. So in terms of Python debugging, you can look at things like spark lines, Python variables, trace points, MDA viewer. So anything that's supported in C, C++, and Fortran is supported in Python. So it's just a normal debugger. And the look and the feel isn't that much different between C, C++, Fortran, and Python codes. Or in terms of the debugger will display the same things. So we also have improved evaluation, so you can evaluate things like matrix objects, array objects, panda data frame, as well as series objects. The only caveat on debugging with Python with DDT is that you need this percentage, a linear underscore Python underscore debug percentage before you run your Python script. And that's just to tell the debugger that it's Python code for it to be able to hook and connect into it. But if you select that, then you're able to debug a Python code. And then DDT also supports offline mode. And so if you don't want to go through the UI or you want to put this into CI/CD, then you can run it in offline mode. And this is quite useful if you're running at very high scales or it's just running for a very long time and you don't want to just keep the UI up there, so you can just run this. And then when it completes, it creates a report and you can view that report in either HTML format or through a text format. Okay, so that's everything on debugging. So I can go through some of the hands-on for that.
Rudy, there is one question on the chat. Can you see that?
No, let me just get the chat up. Okay. Yes, you can modify variable values in GPU kernels as well as CPU. If you go into the stack view and you click on the thread that you're interested in, then it will display all those variables for that thread, and then you can modify those local values. Okay. Can everyone see my screen okay? It should be a command line console with on Polaris. Okay, yeah, thanks, Tim. Actually, before I go into that, it might be worth going through a couple of things, actually. Okay, so because Aurora isn't online at the minute, I can only go through some of the steps you'd use to debug on Aurora. So if you're using SQL code, you can compile it with MPI CXX, and then it's important to do minus lowercase g minus O0, and then you put your application and whatever your application name is. Then a good way to debug is to debug in an interactive session so that you can get the UI and you can just debug within that session. And one of the reasons why you need to run this script is because on Aurora, it has an older version, or at least at the time, it had an older version of one API, and we've been working with Intel to fix some of their issues so that we can debug better. And so eventually this will be the default on Aurora, but for now we have to run the script just to get the latest one API, which gives us access to the latest GDB fixes. Because Forge or DDT relies on the GDB that Intel provides, and any fixes that Intel upstreams, we automatically get into the debugger for those to be fixed. So we work quite closely with Intel, and we raise bugs with Intel, and once they fix it and release a new version of one API, then the DDT debugger improves as well. So once that's done, then there's this setup here, which I can bring. So this is Argon's documentation of how you debug on Aurora. I won't go through all of them, I'll just go through the important pieces. So you have to load Forge, so module load Forge, and then if you're using a wrapper script to map some of the MPI ranks to the GPU tiles, then the way that you set this up with the Forge debugger is you do export Forge debugger wrapper and the location of that wrapper script. And it doesn't have to be this wrapper script. If you run with any wrapper script, this is the way that you run a wrapper script with Forge. So then the other thing that we need to do is we need to enable some of the debugging on each of the nodes. And this is because there's GDB1 API, you need to explicitly enable GPU debugging on all the nodes that you've allocated. And the way that we do this is, I think Argon's written this script, which is a little helper toggle script. If you copy this content that's in the script locally and then run these commands, it will enable debugging on each one of the nodes. So once debug is enabled, then we can just run DDT using this command. So you have to run DDT minus NP, which is the number of processors. If you do minus connect, then you can do reverse debugging. We have to do minus MPI equals generic, and then give in a bunch of MPI arguments, and then the name of the application. Okay, then this goes through how you get the reverse debugging working and connecting to the Intel Z GPUs. But okay, so when Aurora comes back up, it's worth following this guide to get set up with debugging on Aurora.
We have a quick question. I don't know if he's already answered it or not. It's Andrea is asking if the DDT Linaro deploy on the server, or is it for SSH connection?
So there's two parts of it. So there's DDT, which is running on the actual system, and that's installed and deployed on the actual server. But then we have a client, and you can install the client locally, which connects up to that server, and that's through SSH connection. So we connect through SSH from the client to the remote, and that remote is where your application is busy running. But we go through this as we go through the hands-on to explain this in a little bit more detail. Okay, so as I said in the chat, there's a couple of examples. If you click on this Google Drive, then this takes you to all the example files as well as some pre-generated map files, just to get us started. And within there's this Linaro Forge training.tar.gz. So this is the examples we're going to go through. You don't have to set this export Forge training, but it's good to set this because I think some of the scripts is actually using this environment variable. So I'd recommend sending that. Okay, so you don't have to use the Forge client. You could do SSH to Aurora with -X, but that could be quite slow, especially because I'm in Warwick, so I'm quite far away from the system. So if you want to have quite a quick UI experience, it's good to use the Forge client. But if you just can get away with using -X and just connecting to Aurora that way, then that should work as well. Sorry, Polaris, we're connecting to Polaris, then that should work. So I think you already know, but this is the way that you get an allocation. So you do interactive session, queue sub, and then the queue and the account as ALCF training. And then to use Forge on Polaris, you need to do module use soft module files. You have to load the Forge module on there as well as Cray CTI. So the latest version of Cray CTI is 2.19.1. But I tried that early and it didn't seem to be working with Forge. So I've reverted back to 2.19.0. So if you load this module, then it should work. If you do 2.19.1, it won't work. So I need to work out why that is. And then you can look at the user guide as well. So if you want to find out different features that you're interested, just clicking on the user guide takes you there. And then that gives you all the information that I'll go through today. Okay, so this explains the client. So the client is supported on Windows, Mac, as well as Linux systems. And if you're connecting with -X to your remote server, then it could be quite slow. And so what we've done is we've developed a client, and the client sits on your desktop. This connects via SSH to the login nodes. And then as you're busy running your application and you're connecting DDT to that, then it will go onto the compute node. So you're debugging whatever application you're running on the compute node itself, but you're busy viewing this on your desktop. And this is a faster way to debug and profile through the UI. So the only caveat here is that you have to install the client on Polaris. The latest version installed there is 24.0. We're currently on 25.0, but because Polaris is using 24.0, you'll need to install the 24.0 client locally until Polaris gets updated. So I'll bring this across. So you go to linaroforge.com, downloads. So linaroforge.com, then there's downloads and documentation. Because the latest version is 25.0.4, you'll need to go into older versions. And then the second one down, which is 24.0. And depending what you have, I've got a Mac OS, so I can download this Mac OS client. So all this information is in the slides, but I'll just go through it manually as well, how you get everything set up. Okay, so if you put the connection name as Polaris, I've got a SSH config file. So if you click on this one going down, I'm not going to click on it just because I've got quite a few things in my SSH config file, but if you click on that, it should take you to the configurations you set up there. So if you set up to connect to Polaris in your SSH config file, you'll be able to do the drop down to find that. So I can just type in Polaris, which takes it from my SSH config file. And because Forge is installed in this location, you'll need to do /soft debuggers Forge 24.0.5. So that's where it's located on Polaris. Okay, so if we click on that, then we should be able to connect, which is asking for a password. And so what we've done now is we've connected to Polaris via SSH. So the client is now listening on Polaris and waiting for a connection from DDT. And because we've not run anything yet, it's just waiting there until we've connected. Okay, so just to try this out. Okay, so if I do. So the folder we're interested in is this debug one for now. And then all we should be able to do is to run make, which should make all of those examples for us. But as we've seen in the cheat sheet, all we need to do is do module use, module files, and then we need to module load this version of Cray CTI and load Forge, and then we can do this version, and we can see 24.0.5 is installed. Okay, so the next thing that we'll need to do is need to get an interactive session on Polaris. So we do queue sub. Oh, I think have I got an allocation? I think I might already have an allocation. Queue stuff. Yeah, okay. So I've already got an allocation. So if you want an allocation, you run queue sub and you give it a wall time and your queue and your account. So then to connect using DDT, all we do is do DDT, or if you just run this generally, what you'll typically do is MPI exec. Just run this with 4 and then split. So this is how you'd run this application. Normally without our tools, and then to run it with tools, you just append DDT ---- connect. And I'm going to run this with 32 processes. So what should happen if we connected our client up properly, it will just, because we do ---- connect, it's listening on there. If we click accept, then we can run. Okay, I think I might have had too many processes. Let me try the 16 processes. I think I might have just oversubscribed the too many processes. I think I can disable that. Ah, am I in the wrong location? Just give me a second. I'm not sure what's going on. We can try just one more, and if this doesn't work, then I can skip to the Python example, but I'm not sure why that's not working. We can come back to this in a minute.
Are you using the training project or are you using your own project? I wonder if you have a different location.
I'm using the training project.
Okay.
It looks like you're using 2 nodes, right?
Yes, I was using 2 nodes. Okay, I think maybe 2 nodes isn't working, and I need to work on why that is. I can just try to get a new allocation of 1 node. Let's try that. So hopefully this works. 1 node. Okay, that's fine. Let's try with 4 nodes. If this doesn't work, then I'll try the Python one. I think this might be an issue with 2 nodes. I need to work out why that's not working. Let's try with 1 node.
Tim is asking if you need a CPU binding specifier.
That's a good point. Yeah, I think actually you're right. So if you do with 2 nodes, you have to bind the CPUs. That's a good point. But it's busy working on 1 node at the minute, so I can use that. Okay. But I actually want more processors, not just 4. Just try it with 4, just to try that. Okay. 16 should be fine. So let's try 16. Yeah, I tested all this out beforehand on 1 node. So a node works on 1 node. But then I thought I was going to scale this up to 32 processors and try it on 2 nodes without testing it out beforehand. But this should be fine. Let's just do it on 1 node for now on 16 processors. Okay, so as this connects, we're only connecting with 1 node, connected with 16 processors. And what we can see here is that all of these processes have stopped on this line, so line 20. And it's usually this blue highlighting that tells you where you stopped. So for example, what I can do here is I can just step a single process, so process 0. If I step that, go back here, and we can see now there's 2 highlights. And so some of the processes on line 20 and some of them on line 21. And we can see in the stack view where this aggregation is occurring. So if we highlight over that, we can say ranks 1 to 15 is on line 20, and then rank 0 is on line 21. So we can step, like a different process as well, and they go in groups, so we can see where these outliers are. So the stack view is aggregating all the information that it's getting from GDB, and if it's all on the same line, we'll just see 1 line. But if there's a diversion, then we'll be able to see it here. Okay, so what this code is busy doing is it's taking some of these MPI ranks and it's splitting them up into even and odd. So depending on what rank you are, if you're on the even rank, you should go through this execution region here, which is the even comms. And if you're a rank that's odd, you should go into this execution region. So if you run that, you can see this pauses twice because it hit both of these different breakpoints. So we can see 8 processes, so ranks 1, 3, 5, 7, 9, 11, 13, and 15 is on line 44. And then all the other even ranks are on another line, which is here. But as we can see, when we run this, all of these processes as halted. We can change this as well. So we added the breakpoint. All of them is halted because we've put it on the groups being all, but we can set this on specific processes and specific threads. So if we only want to hold, say, on process 0 and then all the other processes go, or if we want to just halt on a specific thread, we can really zoom in and focus in on those specifics. Okay, so if we step now, what we'll see is all of these step at the same time. So we're controlling both this odd comms and the even comms at the same time. But what we might want to do is we might want to control each one of these execution regions at the same time. So what we can do is, if I can find, it should be color. If we compare this across processes, we can see some of them are even and odd. But there's just a quick and easy way just to create 2 different groups. So we've created a group based on all of the odd processes and a group based on all the even processes. And then if you notice the stacks, because we clicked on all, we see all the stacks, but if we click on this green one, we only see those processes on line 45. And if we click on the yellow, we only see those processes on line 74. So what we can do then is we can just step this. And that's only stepping this group and leaving the other group alone. And likewise, we can step this and leave everything from the even group alone. And this is quite nice for finding issues that are race conditions. So you can try different ways of stepping through your code until a race condition occurs. If, for example, you keep running application and say 5 out of 6 times it's fine, but on the 6th time it creates a crash because of some race condition, then you can really find out which of those steps you need to do to hit that race condition consistently. Okay, so this send buffer is all just random numbers that we kind of push into this buffer. So it's random numbers, and we can kind of just evaluate that as well through the send buff. And if we view this array, we can visualize everything that's happening in this buffer. I mean, it's just random numbers, but if you have an application that's got a little bit, okay, need to click on all. But if you have an application that's got more useful information and you want to find a specific pattern in your buffers, then you can use this. But what we want to do here is just evaluate that these are random numbers. We can visualize this as well. You can see there's a range of randomness happening. But what's quite interesting about this buffer is that you can see all of these 0 values everywhere. And this is because this buffer is being inefficiently written. So it's not padding correctly, just writing random numbers in different places you wouldn't expect. And actually, this is a bug in the application when you have your receive buffer being packed with random numbers, and when this gets sent across, it's sending across a range of zeros. So to actually fix this, we need to make this this buffer more compact. But this is a nice way to kind of see this kind of bug and kind of issue where this buffer isn't being written properly. So that's just a quick example of how you'd use DDT. As I said, you can connect processes as well as threads. So if you have OpenMP directives here, and you're running with a number of OpenMP threads, you can run to this line, and then you can step threads. And currently, I've only got 1 thread selected, but if you have, say, 8 threads, then you can step through each of those threads. You can look at the values there to make sure that each one is got enough work, and what each one of these are busy doing. Okay. And then finally, we spoke about trace points. So what we can do, instead of a breakpoint, we can set a trace point. And the things that I want to track is so what you typically do in this scenario is you might write a print statement, and then you have to recompile your code and then connect DDT again. But what we're saying is we can just put in a trace point. Okay, let me get rid of this breakpoint. Okay, so I've written that incorrectly. Okay, so yeah, I'm just printing out send buff, and you can see that these random numbers are just being printed to the output until the application ends. So actually, for you not to do that, let me just restart the session. It's always good practice to put a breakpoint on MPI finalize, just so this doesn't happen, because otherwise your run as your application will end. Okay, this is just connecting again. Okay, so it's always good practice just to put a breakpoint on MPI finalize so that your application doesn't end completely. It will hit this breakpoint. And then usually it's quite good when all of your processes has hit MPI finalize, just to look at your memory and to make sure that you've deallocated everything using the memory debugging. I've not enabled memory debugging in this application, but if you do enable that, you should be able to look at the current memory usage and the current memory stats, just to have a look at how much memory your application is using, how much processes have used that memory, what's allocated and what's deallocated, just to look out for any memory leaks. Okay. So that's a simple HPC type application, but I've also got this ML application which we can debug It's a very simple PyTorch one. So we go into this ML folder. Because there's a Python application and it's using PyTorch, we have to run DDT in a specific way to be able to debug that. So what I'd say as well is I've created this virtual env. Okay, and what this virtual env does is I've created it and then I've pip installed PyTorch. So you need to do that as well. Just create a venv and then pip install PyTorch into that. Okay, so if we run this command, and this is in the slides, you can just copy the 2-layer net.py. There's commands to run that. So we have to do forge stop at main equals 1. And the reason for that is because not all Python code has main functions. And so we're just telling the debugger that this one doesn't have a main function and therefore it needs to use that startup. And we also do forge MPI run equals torch run. So it's telling the it's telling forge to run with this so that it can connect. Then, as I said in the slides, we have to run with percentage a Python debug percentage because it's a Python script. Okay, so if we run that, then we run this with 2 MPI processes. We run in this Python script, so we can just say run. Okay, so this is a very basic neural network. All it's busy doing is it's setting up this network with a range of inputs, outputs, and there's a hidden layer as well. Then all we're doing is we're setting up all the weights with random numbers, and then we're using a bunch of PyTorch functions to update the weights and to do predictions, and it's using this ReLU algorithm to update those weights. But ultimately, what we're trying to do is we're trying to get this loss function down to a small enough number to say that the network has learned. So as it goes through this, it updates things, and then these weights gets updated, and then we print out the loss function. So I've actually got 2 networks here. I know that one doesn't scale, so this one here is just a very small network, which the data doesn't really fit on it, and therefore the learning of this network is quite bad. So there's 2 things we can do. We can write a print statement and just print out what this loss is in each iteration of the algorithm, or we can do this trace point here. And so what I've done is I've created a trace point, and I've done loss.item. So instead of us printing to the output, we can track what the loss is within DDT. And there's a range of PyTorch functions that we can use. So if there's different parameters you want to print out, you can just put in that function into the trace point, and it will print those values out. So for example, if you want to print out what all the weight values are, you can do the weight dot whatever the PyTorch equivalent of that to print this weight values is. Right, so if we run this, okay, it's only running 500 iterations, so we can see in each one of these iterations how this loss function is not that great. You can see it goes up, it goes down, so it's not really learning as well as we would expect it to. So we can look at the trace output as well, and this is just to match things up. So 2979. Can find it. Okay, yeah, I think this is because this is only doing on one process. So this is quite interesting because we're only tracking process 0 with this, whereas the print statement is just printing on both processes. So what is actually happening here is that one of the processes is busy calculating, is busy updating the weight and updating the loss function, but then only much later does the other process kick in. And because we're only tracking process 0, we can see that this is 2979, which matches up with what's being printed on the output. But what we can see here is that this is not really learning that great. So what we can do instead is we can just modify this, and we can give it a better network topology, so that it actually has the size of it is correct with the amount of hidden layers and input layers and output layers for it to be able to learn more effectively. So we can modify that if we save the source file, and then if we restart the session, there we go. So again, if we run this, we can look at this trace output, and hopefully this should start printing some of it on the output. And we can see how it's busy learning, and it's improving a little bit, getting a bit worse. Oh no, it's getting better. Sorry, you can see it's getting better over time, which you should see here as well. If we pause that, we can also inspect some of these local variables and see how everything is doing. So we can look at some of the learning rate. And if we add to evaluations, we can see, well, this is the learning rate that we selected. I think there's so we can look at the devices. So we're only doing this on CPU. We can change this as well to do GPU. I think it's over here. If we change this to GPU, then it will run on the video GPUs. But we can see here, we're just running this on CPU currently. We can change this later. So what's interesting as well here is we can look at the topology. So you can see weight 1. This is running with, is it 64,000? Yeah, so it's running, is there 1,000 hidden layers? Can't remember which way around it is. No, N. Yeah, the hidden layers. So it's running with 1,000 hidden layer, and then in each one of these, it's running, I think this is the output. Yeah, the output dimension is 100. So you can look at the topology of the network as well. So way 2, there should be, again, 100 input layers. And does this go to 1,000? I think it should do. And 10. So 10 input. 100 output. So you can kind of look at the topology of the neural network with this as well. It's not, I think we could probably do some improvements in DDT to be able to see them a little bit better, but this kind of does give more like a rough guide of how your network is set up, just to verify that. Okay, so that's everything I was going to cover on debugging. Is there any questions before I move on to profiling? So the profiling side is not going to be too long, just some slides and just how to get a profile out of Polaris. But I'll just quickly check if there's any questions before I move on.
And Rudy, before you go to the next step, the steps in Polaris is very similar to the steps in Aurora. Is that correct?
To debug, yes, there's a couple of extra steps on Aurora to enable the nodes to debug on Aurora. So there's an extra step just to run a script that enables debugging on all of the nodes that you have allocated.
And do you have that in the Google Drive?
Yes, it's this bit here. Let me.
Yeah, because it would be good if you just go over it so people can see it, even if you can't try it.
Yeah, it's this slide here. Oh, geez, where'd it go? It's this slide here. It's following these documentations here on Aurora. It's this extra step that is required.
Okay.
This copy of the script in the documentation, I think. Yeah, there it is. Helper toggle EU.
That's right. So you do need this helper toggle EU debug. I think that's one of the main step that is required.
Okay.
Okay, so if I go back to the slides. So that was debugging. If we talk about profiling, so everything's is the same. The only thing that's missing here is the Intel Z GPU. So we don't support profiling on Aurora, but we do support it on Polaris. But in terms of languages, startups and compilers and MPIs, it's exactly the same, as well as CPU architectures. So one of the reasons for performance reports in particular is that if you're running your application and you don't know that there's a performance issue, then you could be taking time from the system or just wasting time that you could be using if your application was a lot more performant. And what performance reports does is it gives you at least an insight into your performance to see if there's anything you need to do, because once you see that there's something not quite right, then it's easier to fix rather than keep running the same thing without knowing there are performance issues. Okay, so I'm not going to go over this roadmap, but this is a good way to kind of look at performance and kind of all the different areas. And what performance reports does is it covers each one of these, so I/O, workloads, communication, memory cores, as well as your code is vectorized, and just looking at each one of these pieces in turn. So when you run your application and you run it with perf reports, you get something like this, which gives you some metadata on your application, so how long it ran for. So in this particular case, it ran for 3 minutes. And in those 3 minutes, 20% of the time was being spent in compute. And performance report is saying that this is quite low. Then you're running MPI, so 63.2 of the 3 minutes was being spent in MPI. And performance report says this is quite high. So you want to kind of look at your MPI breakdown. Is there anything you can do to improve that? And so you could reach out for MAP, or you can reach out for another tool that helps you to drill down into your MPI. And then you also find IO communication as well. So saying that IO is quite average, and the time spent in write operations is very low, so we can see what the process write rate is. So there's nothing being read. You're not reading anything in this application, but you're just doing a lot of writes. And so this could be causing some contention on the file system. And actually, if you go back to this roadmap, you can see that IO actually goes before workloads and communication, so it goes before MPI. So even though it's saying you're spending less time in IO, because of the roadmap, that's probably the area that you want to focus on first, because if you get your IO wrong, then it could cause quite significant slowdown. And again, you could use MAP to drill down into your IO, or you can use another IO tool to find out what's going on and why so much time is being spent just doing writes. And then there's a range of other breakdowns as well, and each category has a different color. So your CPU is this light green, and then you have OpenMP, which is dark green. You have MPI, which is blue, and you have IO, memory, and energy as well. If you have things like Python code, then that will come up as pink, and GPU comes up as purple. So just depending on what your application is doing and how it's categorized, you will categorize it as different colors. And so what the CPU breakdown gives is one is single core code. So this tells you how much of your code is running in series that's not been parallelized yet. And usually that's a good place to start. If you've got a lot of serial code running, you want to parallelize that to make more effective use of the hardware. Then you can look at vector numeric ops. That's at 0%, which means that there's an opportunity to vectorize some of your code. And then memory accesses is quite high as well, 78.1. So you could be having inefficient memory accesses. And it could just be inefficient use of the cache. So we can also get a breakdown of OpenMP, and you can look at synchronization. So for example, if you have more OpenMP threads just spending a lot of time synchronizing and not spending their time doing work, that could cause synchronization issues, then you can have a look at that to see how you can make that more efficient. So yeah, so each part of this gives you a breakdown in some values where you can kind of say, is this okay? And what performance reports does as well is it gives you some hints and tips, so you can see that it says there's significant time is spent synchronizing threads in parallel regions, check the affected regions with the profiler. So it's giving you a hint to look at your OpenMP synchronization. Then we have map. And so we talked about the colors previously, but the main point here with map is that it samples on a time base. So your x-axis is time, and so if your application runs for say 3 hours, you would see on the x-axis that whole 3 hours, and then on the y-axis is what those processes are doing over the run of your application. So as I said, orange is IO, light green is main thread, sorry, dark green is main thread compute, light green is OpenMP, and then your blue is your MPI. So what's happening for the first part of this application, it's probably just setting up, doing a lot of IO and main thread compute. And then most of that middle bit, it's doing MPI/OpenMP type operations. So that's the application activity, and then underneath that you see CPU floating point operations as well as memory usage. So we can find a range of metric values that's coming from the CPU, and some of the proc tables as well. And we can put that underneath on a time base to relate it to your application activity. So you can see as soon as your OpenMP and your MPI starts kicking in, we can see the CPU floating point operations kicking in as well. And because we can collect some hardware counters as well, we can look at what the caches are busy doing. We can find other performance type CPU counters to see how those are relating to your application activity. And mainly map is used as a hotspot analysis. So you can see, well, in this area there's a hotspot, so I want to focus on this area and see if I can optimize that. And if that's optimized, you move on to your next part. And these are just some of the highlights. So you can look at things like your peak memory usage, and as your application is busy running, you might have a peak in your memory, and then you can find out which exact line of code that peak occurs in. And then you can use something like DDT to debug around that and seeing if you have a memory leak. You can also look at MPI imbalances. So in this example, some of the time is being spent in this MPI barrier, while quite a lot of time is spent in the MPI send. So, one of your MPI ranks might be finishing early and stuck in a barrier, while all the other ones are still busy running. And likewise, you could have the other effect as well. You can have all of your MPI processes at a barrier, and there's just this one rank that's stuck in this for loop somewhere doing a whole bunch of work. So you can see where this time is being spent in MPI to see where the balances are and relating that to code to make that more efficient. So again, we can also look at OpenMP regions, and if it's gray, that means that there are synchronization occurring. And so you can kind of zoom into that area and seeing, well, what part of this code is making the synchronization occur, and can I make my application more efficient in this line of code? And then there's things like memory accesses as well as vectorization. So if you click on a specific line and there's no vectorization occurring on that line, you could think of ways I can restructure that code for vectorization or for the compiler to vectorize that part of the code. So as I said, that GPU profiling is purple. So the interesting thing here is that purple doesn't necessarily mean time spent in a kernel. It just means that the time is waiting, is the CPU time waiting for the GPU. And the GPU could be running a kernel, or it could be doing some setup. So this particular application, we can see we're running with 3 processors. And just from the breakdown, one process is doing dark green, which means it's doing CPU or main thread compute. The 2 processes are waiting for the GPU, so those could be running the kernels. And we can look at the GPU kernel tab, so we can see we actually have 2 kernels running. This is actually HIP, so it's AMD, but the same is transferable to NVIDIA as well. You'll be able to see kernels and how much time is being spent in each one of those kernels. So we're spending 28.1% of the time in one kernel and 25.4% of time in the other kernel. And as we can see from the main thread activity, we have GPU utilization as well as GPU memory utilization. So towards the mid of this application, it's utilizing quite a bit of the GPU, but there's a bit in the beginning and a bit in the end that's not being utilized. So it could just be setting up and tearing down, but it's a middle bit that's doing a lot of GPU type operations. And then again, we can profile Python code. So if you have ML codes with PyTorch, you'll be able to profile that. But it also has mixed language support. So if you have some Python code calling out to C routines, then you can even profile both the Python and the C routines at the same time. So you can see part of it is doing Python, which will come up as pink. And then part of it might be some C code. And if you have MPI for Pi, then we can profile that as well. It will still come in as blue in the profile. And there's not much you need to do with map. So with debugging, you needed to do percentage. You needed to add that percentage in there, but with profiling, you don't. You just do Python and your Python application. So there's nothing different you need to do for profiling. I won't touch too much on compiler remarks, but this is a feature where if you've compiled your application with a compiler optimization report, then you can import that optimization report into map, and then it'll tell you on which line the compilers have made some decisions. So this could be things like cost models. If the compiler says it didn't vectorize as part of your code because of the cost model it was using, then you can say, well, I don't agree with that, and you can write some directives in your code to override some of the compiler decisions. But this is quite an advanced feature. Then we also have Thread Affinity Advisor. And so this just comes up as you normally profile your application. We have a little toggle that says if your threads are correctly pinned, and it gives some hints and tips if you are spanning some of your threads across NUMA regions, or if you're over subscribing some of your threads. And if it's red, that means that there's an issue, and you can change your slurm command to make better usage of your affinity and to hopefully spread the threads out to help with performance. And the reason why we added this in is because if you have bad affinity, then it kind of silently degrades your performance. And if you don't know that you made a mistake, you can come up with bad performance and not really know why. So just having a quick check and to see, do you have affinity issue is a good check, just to make sure that your threads are correctly bound. And then finally, with map, you can do a diff of two profiles. So one example of this is a while ago, I was compiling with GCC 12 and then recompiled with GCC 13, and I got a big performance gain. And you can actually see which line of code this comes from. And the reason why that performance gain occurred was because with GCC 13, it automatically arranges some of your loops, your for loops for matrix multiplication, so it's in the correct order if you got that incorrect. So just by compiling this with two different versions between GCC 12 and 13, we can see performance gain, and then we can compare those two to see which line of code that occurred. So we have something called alignment points, and so you have to manually align your profile to the different phases of execution. So if you have this for loop, then you put your alignment point around that for loop to see how much that performance gains. So just aligning that profile up, and then you can look at what the difference between memory usage is, your main thread activity, and any memory accesses as well. And you can have as many alignment points as you want. Okay, so that's some of the profiling slides. I've got a very quick demo on how performance reports work. But just before I go into that, is there any questions? Let me just check. Okay, yeah, Tim's already answered the licensing question. Thanks, Tim. Okay. So within that folder, there is this folder called performance. And this is a Python example. So we just do make mil.py.make file. So that should make it, and it's been compiled specifically for Polaris. Okay, then. So I've got this virtual environment, and this needs NPI for Pi. So again, I pip installed NPI for Pi. And just make sure I've got the right modules loaded. Yep, Forge is there. That is there. So the only issue is that this version of Forge, there is a bug, which means profiling, which means I think Polaris got updated recently, which hit a issue with our tools. So this is fixed in 24.0.6. So I need to try to see if we can get a later version of Forge installed. Yeah, because as Polaris updated, it hit a bug in our tools. So that's not going to work with just running map out of the box. So what I've done is I needed to install a later version of map. And then if I just do -- profile, we can run MPI exec. Okay. What I want to do first is just show how you would run this without a tool. So if you run it without a tool, you just run a Python application like that. Okay, that's interesting. So you'd run your Python application with MPI exec, and to run with map, you just append map -- profile. I've had to give it this specific path to get to one of the latest versions of Forge, and that should profile. So it connects to this, and it tells you what your profile is. So it auto-detected Cray Powell's. It's busy running this Python example. And then at the end of it, it's creating a profile. And if I've already got some of these pre-generated. So within that Google Drive, I've already put the map files there. So if I come off of this, I'm just going to open this map file quickly. Sorry, just 1 second. Just opening this file. There we go. Okay, so this is what the profile looks like. We can see that most of this time is being spent on this function there. It's doing a lot of memory accesses. And if you look at metrics, memory, that's quite interesting. I'm not sure. Okay, maybe CPU instructions. Okay, yeah. So the bit that I'm interested in this part is part here. So all of this time is being spent just running this matrix multiplication, and we're spending quite a lot of time in CPU memory accesses. What I've done quite recently is put in some of the user guide information here. So it's saying that high values here are usually inefficient structured code. So this is anything above 98 indicates a problem with caches. And as I said, it's because there's an efficient way that this is being calculated on the cache. So actually restructuring this should help quite a bit.